Welcome to Empowered Learning. This video will be about how to use the chain rule to take the derivative of composition functions. So in this video, what we are going to study is a strategy for how to take the derivative of a function that is stuffed inside of a function. And of course, we call those composite or composition functions. The chain rule is a very abbreviated way of making sure that we have a way to be able to take the derivative of those functions. In short, if we suppose that we have some function and it is a composition function here, where g of x is our inside function, f of x is our outside function, we also assume that g of x is going to be differentiable at any value x that we are dealing with, and that f is going to be differentiable at any value g of x that we deal with. Okay, and of course that means we're implying that g of x is a real number output for the given real number input x. Then we say that the derivative of this composition function is found by taking the derivative of the outside function with respect to the inside function times the derivative of the inside function with respect to x. Okay, now I'll say that again. The derivative of the composition function will be the derivative of the outside function with respect to the inside function times derivative of the inside function with respect to x, or the independent variable the independent variable function. Now, when I do this personally, I don't really tell myself all that. I kind of make it a little bit shorter. This may or may not help you. I'm just going to mention it, and then if it does help you, great. If it doesn't, then just do it the other way. So here we don't really know. We are going to know what this is here, the inside function. But the thing is that when we're doing this particular step, we really don't care what it is. Okay. We don't care how big it is. We don't care how small it is. We don't care how ugly it looks, how beautiful it looks. Care about none of that. To us, it just looks like a variable, and we're just going to use it as that. So for me, I like to say here that the derivative of the composition function is going to be derivative of outside function with respect to blah times the derivative of blah with respect to x. And so for me, thinking of the inside function as blah lets me know I don't care what it is. I'm just going to write it. Okay. And so hopefully that will help you as we go through some of these examples here. Now, we normally have two ways that we go about doing these types of derivatives. One way is in using prime notation. Another way is using Leibniz notation. Okay. And so this is what it looks like in Leibniz notation. And so if we allowed our function here our outside function here to be a function of u, and let our inside function here be a function of x. Because remember here, y is still going to be a function of x here. It's just a composition function. So remember when we said the derivative, and I'll bring this back here. So the derivative of the composition function here is going to be the derivative of the outside function with respect to the inside function. So derivative of outside function, which y is the outside function, with respect to the inside function, which is u, times derivative of inside function u with respect to x. Okay. And so again, if we replace whatever this is explicitly with just u, that's like me saying that it's blah. I don't care what it is. And so what I do here in this first step is I just take the derivative of what I'm looking at as if u was the variable in the first place. Okay. All right. So let's look at some actual examples here so we can see how this actually works. All right. So this will be our first example. We want to find the derivative of this particular function. Now, for this example, I am going to work it both using the prime notation as well as the Leibniz notation as well, okay? Just so that you can see it being done. But for most of this video, I am going to do the prime notation for most examples, just because it's easier to pick up that way. The Leibniz notation gets a little cumbersome when you start to deal with functions that have multiple inside functions to it. But you do want to actually use a Leibniz notation. You want to get used to it, because when you actually have to apply using the chain rule in situations like whenever you're dealing with implicit differentiation, it is very useful to use a Leibniz notation in those instances, because the Leibniz notation lets you know what variable you're taking a derivative with respect to, and it allows you to be able to see when to do what, okay? All right, so for this first example here, if I was to take the derivative of it, I want to take the derivative of the outside function, and right now the outside function looks like e raised to the blah. So the derivative of e raised to the blah is just e raised to the blah, okay? If you remember here, if I said, let's say, the derivative of e raised to the u with respect to u, I'll write it like this. Of course, we know that's just e raised to the u, okay? And u is my blah. So here, first, I take the derivative of the outside function with respect to blah times, now I take the derivative of the inside function with respect to x. And of course, derivative of cosine x with respect to x is just minus sine. So I would have minus e raised to the cosine x times sine x. And that would be what the derivative of that composition function would be. Now, if we were to do this same problem, but we do it using Leibniz notation, we have to set it up a little differently here, okay? So, first thing that we would have to do is we'll have to look at our function f of x here. I'm just going to write it again. What we would want to do here is let's let u equal cosine of x. So if that's the case, then we know that f of u is going to be e raised to the u. So now we can think of the function f in terms of u in this case. And so now if we said the derivative of f with respect to x, that will be the derivative of f with respect to u times the derivative of u with respect to x. So if we look at this, our function here in terms of u is just going to be e raised to the u. And then if we multiply that times the derivative of the inside function, or derivative of u, which is cosine of x, then here we know that the derivative of e raised to the u with respect to u is just e raised to the u. We can multiply that times the derivative of cosine x with respect to x, which is minus sine x. Okay. So this would be minus e raised to the, and if you remember, u is cosine x. And then we will multiply that times the sine x here. And so what you see here is that no matter how we do it, function ends up, or the derivative of the function ends up being the same. All right, so let's move on to the next example. So for this next example here, we could rewrite square root of 4 plus 3x as 4 plus 3x raised to the 1/2. And so from here, you see that the 4 plus 3x is the inside function, and blah raised to the 1/2 is the outside function. And I cannot get this pen to write the way I want here. All right. So for here, we have the derivative of this will just be the derivative of the outside function here. So this would be the derivative of blah raised to the 1/2. So the derivative of blah raised to the 1/2 would be 1/2 times blah raised to the negative 1/2. Because that would be 1/2 minus 1 in the exponent using the power rule, multiplied times the derivative of blah with respect to x. Now, what is blah? It's just the inside function here. So we would have 4 plus 3x here, 4 plus 3x here. And so the only thing that we really need to do now, because this first factor here is pretty much already done, this would be just 1/2 4 plus 3x raised to the negative 1/2. That stays the same. So all we need to do now is take the derivative of 4 plus 3x. Well, we know the derivative of 4 is 0. The derivative of 3x is just 3. So our final answer here, putting it back in root form, is going to be 3 divided by 2 times square root of 4 plus 3x. And again, that's our final answer. 3 times 1/2 is 3 over 2. And of course, 4 plus 3x raised to the negative 1/2 is the same as 1 divided by square root of 4 plus 3x. All right, so for our next example here, we see that we have a tangent of sine of x. And so I'll work this problem up here. So if we take the derivative of this, then of course, we want to take the derivative of the outside function with respect to blah. So of course, the derivative of tangent is going to be secant squared of blah times take the derivative of blah with respect to x. And again, the inside function here is just sine of x. So here, this will just end up being secant squared of sine of x times cosine of x. And this would be our answer for that particular derivative for this function. All right, so let's look at example number 4. So for this one, notice that we have a function stuffed inside of a function, okay? So that means we're going to have to do the chain rule twice here, okay? So just to put some order to this, notice that the innermost inside function is going to be square root of x, okay? So square root of x is inside tangent. And of course, this constant times tangent is an inside function for e raised to the x, okay? So what we actually have here is that y is equal to f of g of h of x here. H of x is going to be square root of x. G of x, h of x is going to be x. g of x is going to be square root of x. No, I still did that wrong. Hold up. Come on. All right. Yep. So here, I could have named, I think what I'm thinking about here is that I could have actually did another one and let x be the innermost inside function, but I didn't want to overcomplicate it. All right, and so so this is what I'm trying to do here. And going to, it needs to be like this. So if we were looking at this in terms of outside function in inside functions, this is the outside function, like the outermost outside function. This is inside function 1. This is inside function 2. Okay. So my point here is that we need to keep up with this whenever we take the derivative of this using prime notation, so that we know when we're actually doing what. All right, so if we take the derivative of this, notice that we're taking the derivative of the outside function with respect to the inside function. So if we start off here, we're taking the derivative of e to the blah. So the derivative of e to the blah with respect to blah is just e to the blah. But then we have to take the derivative of its inside function, which is what we see here. Okay. Now, of course, here, this e raised to the k times tan of square root of x, there's nothing that we are going to be able to do with that. We just leave it as is. But now, when we take the derivative of k times tangent of square root of x, we ignore this constant, but we can take the derivative of tangent of square root of x, and notice that tangent is the outside function and square root of x is the inside function. So here, what we can do is say the derivative of tangent of blah will be secant squared blah times the derivative of the inside function with respect to x. And so now we see that I'm going to have to do one more derivative here, but that's going to be taking the derivative of square root of x. And of course, we know we could rewrite square root of x as just x raised to the positive 1/2. So we just need to take the derivative of that. So I'll rewrite the rest of this. Quite do what I want it to do there. And then the derivative of x raised to the 1/2 is going to be 1/2 x raised to the negative 1/2. And so technically at this point, we are finished taking the derivative, but we want to go ahead and rewrite everything in a nice compact form. So we're going to take that constant k, pull it out in front. And then here we have secant squared of square root of x. And here, this will be divided by 2 times square root of x there. And so that would be what this particular derivative would end up looking like once we got everything written in a compact form. So for our next example, we are asked to find both the first and second derivatives of this function y is equal to e raised to the ax times sine of bx, where we know that a and b are real number constant values and x will be our variable. So notice here that we have a function that is composed of two functions, and those two functions are e raised to the ax and sine of bx. So we can think of this as the u, and we can think of this as the v, where we can use the product rule. Okay. Also notice that both u and v separately are composition functions, where the inside function for the e raised to the ax function is a times x, and b times x is going to be the inside function for sine of bx. So this means that in addition to doing the product rule, we're also going to be using the chain rule. Okay. So let's go ahead and work out this particular problem. Before we do that, I do want to tell you that this problem will get a little long, but the reason why I picked this one is because this particular function here is very important in some STEM applications. To be specific, this particular function is used a lot in what we call enveloping type functions here. So if this value of a is negative, then what you're going to see is this function kind of looks like this. The values of t greater than 0 kind of does like this. And what that models is a function that is a signal rather that is exponentially decaying. So if you think of your voice as a sound with a certain frequency that's going to exponentially decay over time after you say a word, then this particular function could actually model that. Okay, so even though this will get a little long, I just want you to know that for those of you that are STEM majors and you're actually trying to learn this kind of math here, that a lot of times we pick problems here because they show up in applications elsewhere. So we just want you to be familiar with it and see it before you get to those actual courses, or let's say if you're actually doing this at your job, get in a situation where you actually see it. We kind of want you to know or have exposure to it before you actually have to really use it. All right, so we know that for the derivative of this, I'm going to take the derivative of the first function times the second plus first function times derivative of the second. Okay. And for here, if I'm going to take the derivative of e raised to the ax, then realize that the derivative of e raised to the ax is me taking the derivative of a composition function. So I say, what is the derivative of e to the blah? The derivative of e to the blah is just e to the blah times what is the derivative of ax? And of course, we know that the derivative of ax is just going to be a. So I'll leave that and we'll tidy that up in the next step. So plus e raised to the ax. And then here we have derivative of sine of bx, again, composition function. So the derivative of sine of blah is going to be cosine of blah times derivative of the inside function, which is just bx. Okay. So note here that the derivative of ax, all that is just going to be a. Derivative of bx, all that is just going to be b. So here we see that the first derivative is just going to be a times e raised to the ax sine of bx plus e raised to the ax times b. So I'll go ahead and put the b out in front there. So plus b times e raised to the ax cosine of bx. Okay. And so this is our first derivative. Now, if you prefer, we could actually go ahead and factor out the e raised to the ax here for both terms, and you just have a sine of bx plus b cosine of bx. All right, so now what we need to do is find the second derivative. So we'll give us a little separation here. So for the second derivative, we want to take the derivative of the derivative. Okay. Now, for purposes of trying to be as efficient as possible here, I'm actually going to elect to take the derivative of the derivative by using this version here. And the reason I'm going to do that is notice that we start off here by taking the derivative of e raised to the ax times sine of bx. And so notice that I have this here. So by me taking this form, I could reuse what I already have and then just work on taking the derivative of this second term here. Okay. So here I'm just going to say this is going to be a times the derivative of all this business here. I'm going to wait to the very end to go ahead and put this actual answer in there. And then here we'll need to take the derivative of e raised to the ax cosine of bx. Okay. So here, we'll go ahead and just break away from this problem for a second and just work on the derivative of e raised to the ax cosine of bx. And if I was to take the derivative of that, then of course, that would be the derivative of the first times the second plus first times derivative of second and once again we know that the derivative of e raised to the ax, we already found it here, it was just a times e raised to the ax, so we'll reuse that. Let's try that again. And then that's times cosine of bx. And then plus, we have e raised to the ax. And derivative of cosine of bx, we've already done that as well. At least I think we have. No, actually we didn't, so we'll actually do that now. So derivative of cosine of bx, we know that the derivative of cosine of blah is going to be minus sine of blah times derivative of the inside function. All right, and so from there, if we keep going here, we'll see that we have a e raised to the ax cosine of bx plus e raised to the ax, no, minus rather, and because we have that minus here. We're going to have a minus there. And also note that this bx here, when we take the derivative of that, the derivative of bx with respect to x is just b. So that means here we can put this b out in front. So it's going to be a minus b and then e to the ax sine of bx. So now we know what the derivative of e to the ax cosine of bx is. And I'll switch colors for this one. So we'll do that later here. So therefore we have y double prime. This will equal to a times, and now we're going to substitute in what the first derivative was here. Because remember, everything that we had in here was just y, y prime. So if we take this situation here, it's just going to be a e raised to the ax sine of bx plus b e raised to the ax cosine of bx and then plus, now we have b times what we just found out, the derivative of e raised to the ax cosine of bx. So that's going to be a e raised to the ax cosine of bx minus b e raised to the ax sine of bx. And so now at this point, it's just a matter of collecting like terms and trying to simplify as much as we can. So here we distribute our a to both terms here. We'll have a squared e raised to the ax. Starting to slow up again. Let's try this one more time, okay? E raised to the ax sine of bx plus ab e raised to the ax cosine of bx plus ab e raised to the ax cosine of bx. And then we also have this b over here, so this will be a minus b squared e raised to the ax. E raised to the ax. Does not want to act right today. Ax sine of bx. All right. And so now that we have that, notice that these two terms here are like terms, so we can combine those together. And notice that these two terms here are like terms as well. So our final answer here, if we combine these two terms, will just be a squared minus b squared, all that times e raised to the ax sine of bx. And then this will be plus 2ab e raised to the ax cosine of bx. And so you could leave the answer like that, or you could go ahead and factor out the e raised to the ax in both terms, which that is something I would prefer to do. So this would be your final answer. And so this answer or this answer would be an acceptable final answer for this particular question. Okay, so for our next example, we're given a function h of x that is defined in terms of f of x, and we're given information about f of x and a derivative of f of x at a particular x value. And that would be 1 in this case. And what we want to do is find out what the derivative of h is at 1. So first thing we need to do is just find out what h of x, well, the derivative of h of x is. So let's rewrite h of x as 4 plus 3 times f of x, all that raised to the 1/2. Okay. And I'm going to try to make that look a little better because that did not turn out the way I wanted to. All right, so 4 plus 3 times f of x, all that raised to the 1/2 power. Okay, so here we see that the 4 plus 3 times f of x is the inside function, and blah raised to the 1/2 is the outside function. So if I'm going to take the derivative of this function here, I'm asking myself, what is the derivative of blah raised to the 1/2? Well, that's going to be 1/2 of blah raised to the negative 1/2. And again, I'm using the power rule there, times derivative of blah with respect to x. And of course, blah is just whatever the inside function is here. Let's try that again. Okay, and then same deal here, 4 plus 3 times f of x. All right, and so for here, this will just be, I'm going to, just 1 over 2 divided by square root of 4 plus 3 times f of x. And we'll multiply this times on top here. We know that the derivative of 4 is 0. We ignore the 3, and the derivative of f of x is just f prime of x. Okay, so we essentially here just have 3 times f prime of x on top. So now, if we want to find out what f prime of 1 is, we just replace everywhere where we see x with a 1. And then from here, we just use the information that we're given and fill in. So we know f prime of 1 is 4. So that'll be 3 times 4 here. 2 times square root of 4 plus 3 times f of 1 is 7. And so in the numerator, we get 12. Denominator, of course, 3 times 7 is 21. And 21 plus 4 is 25. 12 divided by 2 is 6. And of course, square root of 25 is 5. So our final answer ends up just being 6/5. So for this next example, we're being asked to find the 1,000th derivative of this particular function. Now, I will be honest with you, I have no earthly idea why I would ever need to be able to find the 1,000th derivative of anything. But the purpose of this problem is not to say, well, hey, yes, there's a a reason why we need to find a 1,000th derivative of something. Okay, what it's really trying to do is show you how we can use derivatives to come up with a pattern. And so essentially what we're going to end up doing is finding a general formula for finding a derivative of a function like this. And then from that, we're just going to plug in 1,000 into it, and we'll find out what the 1,000th derivative of it would be. Okay. So just think about the reason for doing this is to find a general pattern or a general formula for taking the derivative of a function like this. All right, so what we are going to do to try to figure out what the 1,000th derivative is we're going to do the derivative of this function several times consecutively, meaning we're going to find first derivative, second, third, fourth, and we're going to keep doing it until we find a pattern that we can establish. And once we do that, we'll use induction to pretty much say, all right, well, this is what the pattern is. This is what I think it is in general. And then after that, we'll plug in 1,000 into the derivative formula for it. And we'll probably have some, constant value or whatnot, or another variable that we can just plug in for 1,000. So we'll come up with that when we get to it. All right, so let's find out the first derivative of this function here. So if we take the first derivative, remember we're doing the product rule. So it's derivative of the first, which is just 1 times the second plus first times derivative of the second. And remember that the derivative of e to the minus x, that is a composition function. So it's going to be the derivative of e to the blah times the derivative of blah with respect to x. And here this is just e to the minus x plus, or minus here, because derivative of minus x is going to be a minus 1. So we're going to do that. Have a minus here, and then x e raised to the negative x. Okay. And I notice here that I am going to have e raised to the negative x in both terms. So I am going to factor that out. And I just have e raised to the negative x times 1 minus x. All right, we'll do the second derivative now. So if I do the second derivative, then I need to do the derivative of the derivative. And so here I am going to, I'll elect to do it in this form here. So if I take the derivative of e raised to the negative x minus x e raised to the negative x, then for the first term, the derivative of e raised to the negative x, well, we already figure out that is negative 1 times e raised to the negative x. So it's just minus e raised to the negative x minus, and now the derivative of x times e raised to the negative x is exactly what we have here. And what I'm going to do is I'll use it in this sense here. So we'll say e raised to the negative x times 1 minus x there. So if we do that, then if I distribute this negative e raised to the negative x to both terms, what I end up having here is negative e raised to the negative x minus e raised to the negative x plus x e raised to the negative x. And so here, notice that I have an e raised to the negative x in all terms. So if I factor that out, notice that what I'm going to be left with here is minus 1, which is a minus 2, plus x there. Okay. Now, if you notice here, we're starting to see a little bit of a pattern here. And if I wanted to have this match what this is doing, I could pull out a -1 here. And so if I pulled out a -1 out of both terms here, what I could actually do is, instead of just factoring out a positive e raised to the -x, I can factor out a negative e raised to the -x. And so that would switch the signs of these. And notice here how what we have for the second derivative is matching very close with what I have to the first derivative. Only thing that's different is I got a 1 here and a 2 here. Here I got a positive e raised to the -x. Here I got a negative e raised to the -x. So really, at this point, you can kind of see the pattern, but just to confirm the pattern, we're going to do both the third and the fourth derivative. So I won't say anything here. I'll just write it out, and we'll see what it is, and then we'll just kind of go from there. And just to kind of make life a little bit more simple for me, I'm just going to write it like this. So for the third derivative, I'm going to take the derivative of the second derivative, and this is a good form of the second derivative to take here. So I'm going to take the derivative of what I got going on here. And this will just be a -2 times, and again, we already know what the derivative of e raised to the -x is, so we'll just write at this point. Again, we already know the derivative of x times e raised to the -x is all of this, so just rewrite. And then we'll simplify. Okay, so we see that that's matching up, and we're going to do the fourth derivative just to make sure. All right, so we see here that it is following the pattern here. So this was the first derivative. This is the second derivative. This was the third, and that's the fourth. So we see that in general here, if I'm going to do the nth derivative, what we see here is that anytime our derivative is an odd derivative, meaning first derivative or third derivative, notice that the e raised to the negative x is positive. Okay. If it's an even number derivative, then it ends up being negative. So how we can denote that is basically we want our odd ones to be positive numbers. We could just say this is -1 raised to the n plus 1. Okay. And so if we let n equal 1 here, then that means that n plus 1 is going to be 2, and -1 raised to the 2 is going to be a positive 1. So that's kind of what we want there. So we'll just call that -1 raised to the n plus 1 to take care of the positive and negative alternating signs there. All right, it's not working. So, all right, so we're going to erase this, and then afterwards we'll go ahead and write the rest. All right, so now that we have that squared away, so of course we have e raised to the negative x, and then of course the nth derivative is going along with whatever number this is here. So we'll just say this is going to be n minus x. So this ends up being our nth derivative formula. And so from that, if we want to find the 1,000th derivative, then all we have to do is plug in 1,000 in for n, and we'll find out exactly what it is. All right. This thing is really not working for me today. All right, and so of course 1,000 plus 1 is 1,001, which is an odd number. So that result would be a negative. And we just have negative e raised to negative x times 1,000 minus x. And that is what the 1,000th derivative of this particular function would be. Okay, so for our next example here, we want to take the derivative of the following function that we have. And one of the things that we want to watch out for in this particular example is this term right here. Okay, this is a relatively simple problem to do, but I've just noticed over time how many students have got this problem wrong because they've kind of gotten their exponential rules mixed up. So I wanted to make sure I went over an example to where you kind of watch out for that. So if we are going to rewrite this function here, of course, our first term will stay the same. Our second term, though, this will be 5 minus, and notice that this is 1 divided by 3x squared. Okay. Now notice 1 over 3x squared means 1/3 times 1 over x cubed. Okay. Oops. I said x squared. That's supposed to be x cubed. Sorry. So this means the same thing as 1/3 times 1 over x cubed, which means this is 1/3 times x raised to the negative 3. Okay. Now, the reason why I'm bringing this up is because I have a lot of students that think that what this is the same thing as this. And that is not correct. Okay. So I know that a lot of times it's just, hey, I glanced at the problem really fast and I just thought it was all together. But we want to make sure that we pay attention to that. Now, the only time that this situation here would be true is if we had parentheses around the 3x like that. So we would have to explicitly write those parentheses in for what we have here to actually end up equaling this. Okay. All right. So this means that we know that this is going to be 1/3 x raised to the -3 and all that raised to the -1. And so this is what we will take the derivative of. All right, so now let's go ahead and take the derivative of our function here. So, of course, in the first term, we would ignore our constant 1/18. And here we see that we have a composition function, so we would use the chain rule. So chain rule says take the derivative of blah raised to the 6, which would be 6 times blah raised to the 5. And then we'll multiply that times derivative of blah with respect to x. And of course, blah in this case is 3x minus 4. Now, for here, oops, didn't mean to write the equal sign there. So now we want to work on the second term, and notice the second term is going to be blah raised to the -1. So if I'm working with that, derivative of blah raised to the -1 would just be -1 times blah raised to the -2. And I say that because if I had x raised to the -1 and I took the derivative of that, that would just be a -1 times x raised to the -1 minus 1, which would just be this. So we're doing the same thing there. And here we would take the derivative of the inside function with respect to x. And of course, inside function, or blah here, is just 5 minus 1/3 x raised to the -3. 5 minus 1/3 x raised to the -3. And so now, at this point, we just need to execute derivatives and simplify. So we have 1/18 here, 6, 3, x minus 4 raised to the 5, and the derivative of 3x is just 3. Derivative of a constant is 0. So we'll just leave it at that. Minus 5 minus 1/3 x raised to -3, all that raised to -2. And now we take the derivative of the inside function here. The derivative of any constant is 0. Derivative of -1/3 times x raised to -3, minus 1/3 times the -3 x raised to the -3 minus 1. All right. So here we know that 6 times 3 is 18, and 18 divided by 18 is 1. So all of this will end up just going to 1. So we'll have 3x minus 4, all that raised to the 5. Second term here, we'll keep that the same for now, for this first factor. And then here we have a -1/3 times a -3, which will give us a +1. And +1 times x raised to the -3 minus 1. That just would be x raised to the -4. So now from here, we'll try to clean up and make this as nice as possible. So this will be 3x minus 4 raised to the 5. And this looks like 1 over 5 minus, and I'll go ahead and rewrite it like how we had in the beginning. So this will be 1 over 3x cubed, like that. And all this will be raised to the 2 to take care of that exponent that's there. And it may not look like it's an exponent, but it is. So let me make sure that I make it look that way. And then, of course, this x raised to the negative 4 is the same as 1 over x raised to the positive 4. So you can write that answer that way. And so at this point, I would say this is probably the simplest that I would try to write this particular answer to this derivative. If we do anything else with it, it would probably not be worth the trouble. Okay, so we will just keep it as is. All right, so let's move on to our final example. All right, so in our final example here, we're going to do something similar to what we did back with example 1, in that we want to actually find out what the derivative of this particular function is going to be by using the Leibniz notation. Okay, and so we're told here what to do. We want to look at our function y in terms of u and let u be a function of x. So essentially what we're saying here is that this inside function here is going to be secant. Okay, so let secant of x be the inside function, and what we're going to do is write this or find the derivative of this function by thinking of it this way. So if you remember here, if I want to take the derivative of y with respect to x, I would first think of the derivative of y with respect to u times the derivative of u with respect to x. And notice here that the du over du here would reduce to 1, so that we just have dy over dx here. So again, that's part of the reason why it's equivalent to do that. So here, if I'm taking the derivative of this function here in terms of u, if I'm calling this u, then this looks like u raised to the 8. So here I'm taking a derivative of u raised to the 8 times, now what I want to do is take the derivative of what u is, which is secant in this case, and I want to take the derivative of that with respect to x. So if I do that for this first factor, I know that u raised to the 8, I take the derivative of it, is just 8 times u raised to the 7. I also know that the derivative of secant is just secant x times tangent x. But of course here I have my derivative of y with respect to x in terms of u and x, but I just need it in terms of x. And so here we remember that the u here is just secant. So this is going to be 8 times secant raised to the 7th power of x times secant x times tangent x. And of course, if we take secant raised to the 7th times secant, that's going to be secant raised to the 8th. And then that just gets multiplied by tangent x. And this is our final answer. And so the derivative of our function y with respect to x ends up just being 8 times secant raised to the 8 times tangent x. And so I hope that this video helped to clear up some things on the chain rule as far as what it is, how to use it, how to think about it, both in prime notation as well as Leibniz notation. Take care.